Hi, and welcome to the Matrix Algebra Tutor. And in this class, we're going to focus on a part of algebra that is sort of compartmentalized. A lot of times you'll learn about this stuff in college algebra. You'll learn about it sometimes at the very end of an Algebra 2 class, depending on your class. And of course, when you're off doing engineering and other things, you'll have a dedicated class in this called linear algebra. At least some of the topics in your linear algebra class will be covered by everything on this DVD, and additionally more things as well. Okay, so the point is, matrix algebra, which we're going to learn about over the next several hours, is very integral, and it's a part of algebra that's very, very useful, and it's a part of algebra that can throw people for a loop, mainly because it looks completely different than anything you've ever learned in algebra once you start dealing with it. I mean, in algebra, it does have the word algebra in the title, so you expect to see a lot of x's and y's and exponents and things like this, but matrix algebra, or matrices, they usually don't have any variables at all. And I think you might have a fair idea of what a matrix is just by thumbing through your textbook. You see these square brackets, and you know that there's some sort of math going on here, but it looks completely different than anything else you probably learned up until that point. And so it looks sort of like gibberish, and it looks like it's going to be difficult. But the fact of the matter is, once you take it one step at a time from the beginning and march through what these things are about, and worry about how to use them and how to manipulate them, just like you had to learn how to manipulate your variables and your exponentials and everything else. We're going to learn about how to manipulate these matrix things, okay? And it's not going to be a big deal. That's the point. So this section of the class is the first section, and what we're going to learn about mainly is what is a matrix, okay? Let's write it down, let's talk about its components, let's get comfortable looking at them. We're not going to be adding anything or subtracting anything, we're just going to learn about what a matrix is and why they're useful, okay? So let me start with the first thing, the motivation. Why do we care about matrix algebra? Why do we make it a point to learn matrix algebra, okay? Well, let me ask you this. When you remember back to your algebra from a long time ago, at some point you did study something called solving a system of equations. That's what you studied. It's covered in my DVDs. It's covered in every algebra class that you're going to take, whether it's college algebra or algebra 2 in high school or whatever. You will study something called solving a system of equations. That's a big fancy thing, and all it means is, if you remember back, you have instead of just one equation to solve, like x, plus 2 is equal to 9, that would be one equation. A system of equations is usually more than one equation and more than one variable. So for instance, you might have, instead of one equation, you might have two separate equations, and because you have two equations, you're trying to solve for two unknowns, okay, x and y, let's say. Or if you want to have a more complicated problem, you could have three variables you're trying to solve, x, y, and z, and because you have three variables, you must have three equations in order to solve for all the variables. So the long and short of it is, you have to have as many equations to describe the system you're talking about as variables you're trying to solve. So as a practical example, let's say in this room, this gas, this air around my head right now, okay, it has a certain temperature. Okay, it has a certain pressure. The pressure goes up and down with the weather, depending on the cold fronts and warm fronts that come through. And it might have a certain humidity, let's say. So those are three variables. We could call them x, y, and z. But if you're solving a real problem, you might actually have a problem that deals with the pressure of some gas, the temperature of some gas, and let's just say the humidity of the gas. So three variables. And you might have three equations in order to solve those three variables. So what you would do, you would write down the equations that describe the system, and you'd have to have three different equations to solve for those three variables if that's what you were trying to do. And you were taught several different ways to do that. You were taught, if you remember back from algebra, you were taught how to solve that by substitution. You can take one of those equations, you can solve it for a variable, plug it back in another equation, and by doing a lot of substitution over and over again, you can eventually solve for one of these variables and continue solving for the remaining variables, so you can use substitution. You also probably learned something called addition, solving them by addition, or sometimes it's called solving them by subtraction. Basically, that is just taking the equations and lining them up one under another, and you can long and short of it is, you can subtract them from one another, and by doing that, you end up eliminating some variables and solving for some variables, okay? So what am I leading to? Why am I taking you down this memory lane of algebra that you've studied, before? Because solving a system of equations, which is just simply more than one equation, and of course more than one variable because you have more than one equation, okay, you already know a few techniques to solve those things. You've already done that before. The main use of matrices, okay, the main use of matrices, or matrix algebra, is doing that, solving a system of equations in a shorthand, fast way. That's really what it is, okay? So if you have to take one thing away from this section, at least in the beginning here, the entire point of this entire DVD course is not just to bore you with a bunch of matrices on the board, it's because it has a point. And the point is you can use this matrix stuff to solve systems of equations that are very useful to learn how to solve in real life problems, okay? And you can do it without all that substitution, without all of that equation addition. You're going to use it, solve it using matrices. And you're going to find out that once you figure out how to crank through it, it's going to be actually not too bad. And it's going to save you time because it's just going to save you from writing down a lot of other steps. If you remember back, solving those systems, it took a fair amount of paper to do because you're writing all the equations down every time and solving them. With a matrix, once we show you how, it's not going to be a big deal, okay? So that's where we're going. That is the end game. The first few sections of this course are going to teach you what a matrix is, how to add them, subtract them, and everything else, sort of leading up, giving you the skills, so once we get to the middle of the class here, the DVD, you'll learn how to actually solve systems of equations and understand what these things are for. Now, matrices have uses far beyond that, but that is certainly the most important thing for you to remember now, and certainly probably the most practical reason that we use them. And computers use matrices to solve these things all the time. If you're going to write a computer program to solve a real problem for more than one equation, you're definitely going to use a matrix to solve it. No question about that, okay? So let's finally dive into the topic here and figure out what a matrix is, okay? The big deal here is a matrix is nothing more than some rows and columns of numbers, okay? For a minute, even though I've kind of given you the end game of where we're going, that we're going to use these matrices to represent a system of equations, just forget about that for now. Just put it in the back of your head and remember that's what we're going to use these things for. But for now, just open your mind and learn about what a matrix is. And it's simply a square bracket with some numbers inside, okay? It's not that big of a deal. So let's write that down. Okay, a matrix contains rows and columns of numbers. Now, notice I didn't say that it contains variables. I didn't say that it contains exponents. I said it's rows and columns of numbers. So when you think about that, even though they might look a little funny at first, and we'll get to that here in a second, it's really just some brackets filled with numbers. And you've been dealing with numbers ever since you were a kid. So, even though it looks foreign to you at first, it's not that bad. There's not a bunch of variables running around here for you to keep track of with a matrix. Usually, you're going to be dealing with numbers. And numbers are much easier to wrap your brain around, usually, than a foreign concept with variables. Okay? So, what is a matrix? The easiest way to do it is just to write one down. Okay? Here is what a simple matrix would look like. You put a square bracket, and there's some numbers inside. Let's put 1, 2, 3, and 4. Okay, congratulations. We've just written your first matrix down. Okay? Now, the first thing most people want to do when they first learn about matrices is you'll see these numbers here, and it's confusing. There's no addition, subtraction, division. There's no operation in here, so it looks a little bit odd. There's no equal sign anywhere. Okay? And it's a bunch of numbers, but it just doesn't look like it's very useful, okay? And what you have to remember is, just like when you first started algebra, you have to learn the basics of this stuff in order to be able to use it for what it's really intended, okay? Just like you had to learn what a negative number was, and that was a really complicated thing way back in the day, well, you're going to have to learn what these things look like, okay? So these things are called matrices, and notice that there's some rows. There's 2 rows in this matrix, and there's 2 columns in this matrix, okay? So you see here that you have 2 rows in this matrix, and you have here 2 columns. Okay? Whoops, got to spell columns right. Okay? 2 columns. 2 rows and 2 columns. Why is that important? Because you'll see later on that when we write different types of matrices, you can have different numbers of rows and different numbers of columns. So generally when you're writing these things down, you refer to the order of the matrices, or the order of the matrix, just to describe how big it is, what its shape is. Okay? So what you would say in this case is that the order of this matrix which you'll probably have to do in your test. You'll be given a matrix and it'll say, what's the order of this matrix? And you'll be like, what is that? Well, you have to learn the definition. The order basically just says how many rows, how many columns. Okay? The first number is the rows, and the second number is the columns. Okay, so this is 2 by 2. The x is not a variable x. It's like a 2 by 4 piece of lumber or something. That's what the x means here. So it's a 2 by 2 matrix, 2 rows and 2 columns. So you see, this is not rocket science. Okay, there's no variables here. There's nothing complicated here. There's some numbers inside of a bracket. Now, the only thing you might beat your head against the wall trying to figure out is what would this possibly be used for. I've already given you the punchline. You see, this matrix. Later on we're going to learn, this matrix can be used to represent an equation. Actually, it can be used to represent a system of equations, just like you were solving those systems of equations when you first learned algebra, right? And we're going to use these matrices to solve them easier, to basically solve them easier, and that's really what it's all about, okay? So this is a 2 by 2 matrix. That's called the order of the matrix. If you have a question on your test, what's the order of a matrix? You write down how many rows, how many columns, put an x in the middle, and you read it 2 by 2 or 3 by 2 or 5 by 4 or whatever. That's the order of the matrix, okay? So let's go ahead and write down what the order of a few other matrices would be, just to get a little bit of practice, okay? Let's say we have a matrix that looks like this. 0, -1, 3, 0, 1, and 4. Notice I do have a negative number in here. Notice I do have some zeros in here. So I said the matrix is usually going to be full of numbers. These numbers can be negative, positive. They can be decimals. They can be fractions. It can be any number that you want, really. Any real number. That's what we're going to use these things for, okay? The zeros are here. We still have to put them in their place, okay? And again, this would represent, I'm giving you the punchline a little bit. Later on, we'll see that this represents a system of equations, okay? That you would then use this matrix to solve, okay? So that's where we're going with this. If you were trying to find the order of this matrix, all you got to do is look and say, well, look, it has 2 rows by 3 columns. 1, 2, 3 columns. So it's a 2 by 3 order. 2 by 3, okay? So that's another matrix. And just to give you a little bit more practice, let's go ahead and write another one. Let's switch colors a little bit. What if I have, notice I'm kind of drawing a kind of a vertical skyscraper matrix here. 1, 3, let's see, 74 just for kicks, 29, let's say -5 and -1. Okay, so we've got some big numbers, we've got some negative numbers here, but again, it's the same thing. What is the order of this matrix? If you were asked that on your test, you would say, well, how many rows do I have? I have 3 rows, so that number goes first, and 2 columns, so it's a 3 by 2 order. Okay, so we haven't really done anything with these things yet. We've just talked about the fact that we have this thing called an order, which is the number of rows and the number of columns. Okay, and that's sort of just a definition more than anything else. We haven't done any operations with these things. We're just writing them down. You have no idea at this point how you would use this thing to solve a system of equations, but that's fine because we will get there. Okay, we will get there. Now let's continue learning about a matrix and learn about the elements of a matrix. Okay, that elements sounds like a complicated thing, but really, when you look at this matrix here, it has numbers inside, and each number inside of this thing is called an element of the matrix, okay? So this entire entity is called a matrix, and everything inside of it, every single number, is called an element of the matrix. So if you're asked to find a certain element or pull out a certain element of a matrix to identify it, just on a test to see if you know what you're talking about, you know that you're going to be looking inside this thing, try to pull a number out. That's what you're going to be doing, okay? So the elements of a matrix, the elements of a matrix are the numbers inside. Okay? The numbers inside, okay? So, let's go ahead and draw that. The easiest way to do this is by example. Okay, let's say you have, well, let me start back over a little bit here and say that usually in your textbook, you will see the elements of a matrix written as the letter A, usually, not always, with a subscript I and a subscript J. Okay, now this is usually when people start to get confused about this matrix stuff, because you have some variable, and you have two little subscripts. What does all this stuff mean, okay? This is just used to identify what element of the matrix you're talking about. And it's very, very simple. Let me show you what I'm talking about here by an example. Let's say we have a matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. Before we go any further, what would the order of this matrix be? Okay, just think about that. You have to look at the rows and the columns. There's 3 rows and there's 3 columns. So it's a 3 by 3, 3x3. It's a 3 by 3 order matrix. Okay. Now the elements of the matrix are identified by A. Usually the books use A with a subscript I and a subscript J. Don't get worried about this. Okay. All it means is this number, the first one, the first subscript, identifies the row that you're talking about, and this number identifies the column that you're talking about. And once you've identified the row and the column that you're talking about, you can identify any number uniquely in here, okay? So all you're doing is to pull out an element or to identify an element of a matrix, you're going to generally have represent some variable, really just to show that you're talking about an element of a matrix, and you're going to have 2 little subscripts. The first subscript's going to identify the row you're talking about. Is it this row, is it this row, or is it this row? The second number is going to talk about the column that you're referring to, and the intersection of those 2 things is the element you're talking about. So to put it in more concrete terms, let's practice. Okay? Let's say I'm trying to find element A sub 1, 1. On a test, you're given this matrix and you're told or asked, what is the element denoted by A1, 1? So all you have to do is realize the first number is the row, so it's the first row. This is row 1, row 2, and row 3. This is column 1, column 2, and column 3. So you're in row number 1 up here, okay? Now, in order to find out what element you need, which is what number you need, you're in column number 1. So this is column number 1, this is row number 1, so this guy right here is the element you're talking about. So you see how easy this is. You just have to know how to interpret it. You look at the row, you look at the column, that's the element you're talking about. Because frequently when you're dealing with a matrix, you might have to refer to the elements of the matrix. You might have a need to write an equation involving the elements of the matrix. So this little subscript notation is how you do that. It's like a crossword puzzle. I mean, really, it's no different than a crossword puzzle. You know, 3 across, 2 down. I mean, that's really all it is. Row and column. That's how you identify the elements of the thing. Okay. So, what if you were trying to find A1, 3? Okay. A1, 3. First number is the row. So I'm on row number 1. Second number is the column. Column number 3. So the element is 3. Okay. Let's say I had to find A2, 2. Okay, A2, 2. And by the way, when I say A here, and A here, that's if I'm calling this matrix A, okay, I could be calling it that, labeling it matrix A, then these little subscripts denote the elements of the matrix A. Okay, that's why if you were going to call this matrix, matrix B or matrix Z or matrix G, then you would have G with the subscripts 1, 2, 1, 3, whatever. Depending on what you actually labeled the thing. We're just using A because it's easy, okay? So, row 2, column 2. Here's row 2, here's column 2, intersection is 5, okay? A2, 3, row 2, column 3. Here's row number 2, here's column number 3, that's a 6, okay? And then let's say A31. I shouldn't say A31, it's A31. It's not really the number you care about, it's the individual digits here. So row 3 over here and column number 1. Intersection is 7. Okay, and finally, let's say I'm going to find A32. So I look, the first digit is the row, the second digit is the column. So the first digit is row 3, so I'm in row 3, column number 2, this is column number 2, the intersection is 8, so the answer is 8. So we came up with 1, 3, 5, 6, 7, and 8. And basically you can do this for any element of the matrix. If the matrix had, let's say this matrix was huge. This matrix could have, 100 rows and 519 columns. I don't know why you would ever need to create a matrix that big, but you could if you wanted to. And so in order to look at the individual elements of that matrix, the individual numbers, all you need to know is two numbers, the row it's on and the column it's on. Once you have that, you're in good shape. So this is a good introduction to matrices. Here in the rest of this section, we're going to talk a little bit more about when matrices are equal, when the different matrices are equal, and just get a little bit more practice with identifying the elements of the matrix here. Okay, now something else that's very important to understand about matrices. We have drawn actually several matrices so far. Some of them have the same number of rows and columns, and so they're called square matrix. I don't even think I mentioned that before, but that's something that you probably need to remember. When it has the same number of rows and columns, it's going to look like a square. That's called a square matrix. Okay? If it has different number of rows and columns, which can always be the case, and it's a non-square matrix. Okay, that makes sense because it looks more like a rectangle, right? And the thing that you need to remember is if you have two matrices and the test or some book asks you, are these matrices equal? Are they equal? Basically, all you have to remember is a matrix is equal to another matrix if and only if they have exactly the same shape and size, in other words, same number of rows, same number of columns, and every single element inside those matrices are equal to the corresponding element in the other matrices. So basically, they have to look exactly identical in all respects. The size, the shape, and exactly every little element inside, they have to match exactly, otherwise they are not equal. Okay? So let's write that down and get a little practice. So we say that two matrices are equal if they have the same size and shape and all elements are equal. Now, notice here I wrote something down. They have the same size and shape because, you know, that to me is everyday language everybody's going to understand, okay? Basically what this means, and you'll see this a lot in your book, let me just go ahead and put a dotted line around it. Same size and shape. This is my language, my layman terms. It basically means the same order. Remember, we wrote down the order. 2 by 3, 3 by 2, 4 by 6, that was the order. Basically, they have to have the same number of rows and columns, and so that means that they're going to have exactly the same order. It's the same thing as the same size and shape, but I just like the way that sounds better. Okay, so let's look at a couple of examples of matrices that are equal or not. Let's say I had these two matrices, 1, 2, 3, 4, 5, 6. Notice this matrix has 3 rows, 1, 2, 3, and 2 columns, 1, 2. And I have another matrix. Okay. And again, I have 1, 2, 3, 4, 5, 6. Exactly the same numbers inside. Let me ask you this question. Are these two matrices equal to one another? Are they equal? Okay. Well, you notice they have exactly the same numbers. 1, 2, 3, 4, 5, 6. They're all the same. But they do not have the same size and shape. So these two things are not equal to each other. They just aren't. Okay. It doesn't matter if they match exactly element for element. You can go across reading them. If they don't look the same, they don't have the same size and shape, they're not equal. Okay? They have to look exactly the same. This guy has 2 rows and 3 columns. Obviously, that's different than the 3 rows and 2 columns from before. So those are not equal, okay? Because they have different shape, basically. Okay? So let's look at another example. Let's say you had a matrix that was a square matrix, and it was 31 inside and 79 inside, 0 and 31. And I'm going to write down another matrix, and let's see if they're equal. 31, 79, 10, and 31. And I ask you, based on this definition above, are these two matrices equal? Well, 31 matches, 79 matches, 0 does not match the corresponding element. Okay, and 31 does match, okay? And notice in this case that both of these are 2 by 2 matrices. 2 rows, 2 columns. 2 rows, 2 columns. So they're both 2 by 2, they both have the same order, and they both have the majority of the elements the same, but they are not equal. And the reason they're not equal is precisely because the 0 does not equal the 10, okay? So you see what I'm saying here is that when you try to look and see if two matrices are equal to one another, they have to look the same as far as the same shape. They have to have the same number of rows and the same number of columns, and the corresponding elements here in every single place must be the same. If they are not the same, then they're not equivalent. That's just basically it. Okay. Now let's look at another one. Let's say I have 7, 3, 4, negative 1, 2, 3. Okay, that's a matrix. And let's put another matrix down with some different elements inside. 7, 3, 4, negative 1, 2, and 3. And I ask you, are these two matrices equivalent? Well, they have the same number of rows and columns, 2 rows, 3 columns, 2 rows, 3 columns. 7 matches with 7, 3 with 3, 4 with 4, negative 1 with negative 1, 2 with 2, 3 with 3. Because they have exactly the same size and shape, because every single element is exactly equal to the corresponding element, these two things are exactly the same. They are equivalent. Okay? And just to drill it home a little bit more, 1, 3, 9, 7, 2, 4. Is it or is it not equal to 1, 3, 9, 7, 2, 4? Okay? I hope you can see at this point that these guys are equal. Okay? They have the same number of rows, 3 rows, 3 rows, 2 columns, 2 columns, and everything is equivalent. 3 with 3, 9 with 9, 7 and 7, 2 with 2, 4 with 4. Okay? If any one of these numbers did not match the corresponding number, just like in this case up here, they would not be equal, but because they have the same number of rows and columns, and because every single corresponding entry is the same, they are equal. So that's pretty important, because a lot of times you'll be asked, is this matrix equivalent to another one? Are they equal? Okay, and you'll just have to go and look and make sure that they have all the same elements and everything else. So you see there's not much math in this yet. I mean, it's not that hard. There's some numbers in there. We're just learning about what the matrix is. Later on, we'll learn how to add them and subtract them and go about our business there. Okay? And by the way, just to give you a prelude, adding and subtracting matrices are really, really simple. Multiplication is a little more involved. That's going to throw you a little bit for a loop later. Adding and subtracting is a piece of cake. You'll do that in your sleep, okay? So for the following problems here, let's do two things just to get some practice. Let's give the order of the matrix, okay? And let's also, we want to find A3 sub 2, and we want to find A sub 2 sub 3, if we can. A32 and A23. If possible, let's find those, and if it's not possible, let's go ahead and look and see why it's not possible. So for the first problem, let's go ahead and just write the matrix down. And the matrix that we're going to be given here is going to be 4 and negative 7 and 5 and negative 6 and 8 and negative 1. That's my matrix. So the first thing we want to do is find the order. Okay? Well, we see right away that we have 2 rows, and we also see that we have 1, 2, 3 columns. And if you remember, the order of a matrix is the rows with this x here, meaning 2 by 3. Rows comes first, then columns. So the order is 2 by 3. Okay? Order is 2 by 3. Now let's try to go ahead and do the second part. Let's find A32 and A23 if possible. What is A32? A sub 3 sub 2. First number is the row, and the second number is the column. So we have to go to row 3. Row 1, row 2, there is no row 3. Okay? Because there's no row 3, this makes no sense at all. So this does not exist. Or you can say it's not possible to find it or whatever. It's because this matrix only has 2 rows. So you can't find A sub 3, 2 because you're trying to find something in the third row. There is no third row. So you put that it doesn't exist. Now A sub 2, 3 we're going to be able to find. Okay? First number is the row, second number is third column. So row 2, third column here. So the intersection is negative 1. Okay? A sub 2 sub 3 is going to be negative 1. So that's just what we're doing. We're getting a little bit of practice with doing these things, identifying the order of the matrix, getting comfortable looking at them, and then pulling out, you know, an element here just to get a little bit more practice with it. Let's say our next matrix is a big matrix, 1, negative 5, pi, e, 0, 7, negative 6, negative pi, negative 2, 1/2, 11, negative 1/5. Now, part of my motivation for breaking this section out kind of by itself is just to get you comfortable looking at these matrices, okay? This is a collection of numbers. Don't be scared off by the fact that there's pi in here, or negative pi. I mean, these are just numbers too. 3.14159, on and on and on. That's a number. E is also a number that you remember back from algebra. 2.71, la la la, it goes on forever, okay? 1/2 is a number, negative 1/5 is a number, they're just fractions. So there's nothing weird here. They're all numbers, just because they have a couple of things, pi and e. I mean, that's just depending on what your system of equations that you're trying to solve that we're going to learn how to do later is. You may or may not have some goofy looking numbers in there, but for the purpose of this example, it's just an abstract thing. We're just looking at the matrix. So how many rows do we have? We have 3 rows. 1, 2, 3 rows. Okay, how many columns do we have? 1, 2, 3, 4 columns. So because we're trying to find the order of this matrix, we will say that we have a 3 by 4 order. Because the rows always come first and the columns always come after that, 3 by 4, okay? Now, after we find the order, let's go ahead and try to find A sub 3, 2. Okay, again, the first number refers to the row you're on, 1, 2, third row. Second number is the column. Here's first column, here's second column. Third row, second column, just like a crossword puzzle, 1/2. Okay? And finally, A sub 2, 3. Okay? First number is the row. We're on the second row. This is the column, 1, 2, 3. Second row, third column, negative 6, just like a crossword puzzle. Okay, so these are the 2 elements, and you could be asked on a test to find, any element here, and you'll know how to do it. You basically just look at the intersection of the row and the column, and you can pull out any element of a matrix, and that's how you represent it with these little subscripts. So when you first look at this, though, in a book, especially when you flip open the page to matrices, you'll see a bunch of square brackets and a bunch of stuff in there, and then subscripts with I and J and maybe some numbers, and it just looks confusing. This is like a crossword puzzle. That's all you're doing. You're finding the intersection to pull out the element that you're interested in. Okay, now in this set of problems, what we want to do is we want to find the value for the variables, and you'll see what I mean again in a second, that make the matrix equation true. Okay, so don't be worried about this, okay? It has a lot of fancy words. The variables that make the matrix equation true. It sounds crazy, but let me show you what we're doing, and it's not going to be a big deal at all. If on a test, and frequently you're given questions like this, is why I'm doing them. Let's say I have 2x in here. Let's say I have negative 4 in here, 6, negative 3y. And let's say that they're claiming that this is equal to the matrix labeled by negative 10, negative 4, 6, and 6. All right, and the question is, what values of x and y are needed to make this matrix equation true? Let's step back and look at what we have here. This is a matrix equation, a simple matrix equation, okay? It looks complicated, but really all it means is you have a matrix here and you have a matrix here, and we're claiming that they're equal to each other, just like when you looked at equations back in Algebra 1, we had the left side, which had x's and y's and exponents and division, everything else. We had a right side, and we were claiming that they were equal. And a lot of times you were just solving for the value of x and y that made them equal in your basic equations from Algebra 1. This is no different. I have a matrix here and a matrix here, and I'm claiming that they're equal. I just need to figure out the values of x and y that make them equal. Okay? Now also, earlier I told you, most of the time matrices you're going to be dealing with numbers and not variables, and that is true. That doesn't mean you cannot have variables in here. I'm just telling you that most of the time your matrices are just going to have numbers inside, and that's true. But in this kind of problem, usually they're trying to throw you for a loop a little bit and trying to make you think about what this means, okay? Remember the fundamental thing about matrices. If they're equal, the only way they can be equal to each other is if they have the same size and shape, which they do. 2 rows, 2 columns. 2 rows, 2 columns. So they have the same number of rows and columns. And every single element must be the same as the corresponding element. Negative 4 is equal to negative 4. 6 is equal to 6. So you see, the only way these two things can actually be equivalent matrices is if this element is equal to negative 10 and if this element is equal to negative 10. So all you have to write down is 2x is equal to negative 10, and also negative 3y must be equal to 6. This element must be equal to this element. This element must be equal to this element. If that is true, then that means that these two matrices really are equal to each other, which we're claiming that they are. So now you just solve for x. I think you should know that you just divide by 2 on both sides, you get -5. And then here, y, you're going to divide by -3 on both sides, so you're going to get -2. So if x is equal to 5 and y is x is equal to -5 and y is equal to -2, if those two things are true, then this matrix is equal to this matrix. If x and y have any different values than that, those matrices are not going to be equal to each other. So that's a very, very simple matrix equation. All it means is you have a left side and a right side with matrices, and they're equal to each other, and you're just solving for the values that make them equal. So the corresponding values, the corresponding elements, I should say, have to be equivalent. So you set up little mini equations here and solve them for x and y. It's a very common test problem. Let's do another one. Let's say we have a little bit bigger. We have x plus 3 over here, 2w minus 8, y plus 1, 4x plus 6, z minus 3, and 3z. This is a matrix, okay, with some elements inside. I just happen to have more complicated elements. There are expressions in there. And I'm claiming that this matrix is equal to this one over here. 0, -6, -3, 2x, 2z plus 4, and -21. Okay, so I have two matrices, and I'm claiming they're equal. They do have the same size and shape. Now remember, this right here, this is an element. This thing here, this is an element, this is an element, 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 element. Even though they have pluses and minuses, I mean, this is an element here. So I have 3 rows and 2 columns. I have 3 rows and 2 columns. So they do have the same size and shape, and in order for them to be actually equal to each other, that means every element must be equal to the corresponding element over here, just like in the simpler examples we were doing before. They all have to be equal. So all you're going to do is you're going to write down some little equations and solve them for the values of x and y and z and w to make these two matrices equal to each other. So let's do that. And you're going to see it's not a big deal. X plus 3 must be equal to 0. It has to be, because that's the only way these two matrices can actually be equal to each other. So to solve this thing, you just say x is equal to -3. Move the 3 over to the other side. Okay, you've already solved for one of the variables. Okay, let's go to this one here. 2w minus 8 has got to be equal to -6, because this is a corresponding element. So what you'll have is 2w is equal to moving the 8 over here. So you add 8, getting rid of this over here, you add 8 to this side. -6 plus the 8 that you're adding over here is going to give you a positive 2. Okay, and then to solve for w, you divide both sides by the 2, and you're going to have a 1. Okay, so w is going to be equal to 1, and you circle that as an answer. So look, you're already making progress. Over here, y plus 1 has got to be equal to this element right here, which is -3. Okay, and to make it happen, you move the 1 over here, so you subtract 1 from both sides, and you're going to have -4. Move the -1 over, -3 minus 1 gives you -4. Okay, and looking over here, you'll have z minus 3 has got to be equal to the corresponding guy over here, which is 2z plus 4. Okay, now let's see if these are equal. Let's go ahead and move this 3 over here. So I have z is equal to 2z. Add 3 over here. 3 plus 4 gives me 7. Okay. Let's move the 2z over here. We're going to subtract it from both sides. I'm going to have -z is equal to 7. Subtracting 2z over here, subtracting 2z over here. And then finally solving for z, you're going to have z is equal to -7. Z is equal to -7. Okay. So I think we've actually found all of our variables, because there was x, y, z, and w. We found x, y, z, and w. Okay, and we've equated this with this, this with this, this with this, and this with this. But you know, we can continue. Doing these just to make sure that we check ourselves correctly. Let's say we wanted to do this one just to make sure it was right. We would have 4x. We've already solved for x, so we really don't have to do this. But we could say that this element is equal to this element just to double check ourselves. So the way you're going to do it is you're going to, let's say, move the 4x over here. So you're going to have 6 is equal to, subtracting 4x from both sides, you'll have negative 2x. 4x minus negative 4x on both sides, so you have 2x minus the 4x, giving you negative 2x. And then x is going to be equal to, dividing by negative 2, you'll have negative 3. Okay? And notice that x is equal to negative 3. By that equation, that's exactly what we found up here. It makes sense. There can only be one value of x that makes these things equal. So you really don't have to do these, but we're doing them to check ourselves, really. This element's the only one we haven't done. It has to be equal to negative 21. So we have 3z is equal to negative 21. And you just divide both sides. Z is equal to, divide both sides by 3, you'll have negative 7. Okay? Z is equal to negative 7. That's exactly what we found here. Z is equal to negative 7. So, this is really a duplicate of what we've done here. This is really a duplicate of what we've done here, but we do them all just to make sure that we got the right answers. Okay? And in this case, basically all you're doing is finding the values of x, y, and z, and w that make each element equal across the board. And then for these values, these matrices really are equal. If these variables have any different values than these, then the elements will not be the same, and so these will be totally different matrices. Okay? So in this section, we've covered a very important topic. We've introduced you to the concept of a matrix. Hopefully it's not as scary of a thing as it maybe was a little while ago. It's basically a collection of numbers. You can have variables inside, yes. Most of the time you'll see in the rest of the class that you're dealing with numbers. That's all that's going to usually be in there. And I've given you the punchline. What we're going to do with these things is we're going to use them to solve systems of equations. And you're going to find out that they're not a big deal. And it's actually easier to use them to solve systems of equations, especially large systems, than it is to do it by hand the other ways that you've learned in your basic algebra. So as a roadmap ahead, we're going to learn how to add these things, we're going to learn how to subtract them, we're going to learn how to multiply them, we're going to learn how to solve equations and systems of equations and go on from there. So it's a good introductory section. Watch it a couple times if you need to. We're going to baby step our way through it, learn the operations, learn the properties of the matrices, and then of course we're going to solve systems of equations with them, which is really the main point, at least in this course, of using matrix algebra.